Now we'll see another example of dynamic programming, that is knapsack problem. This knapsack problem already we have discussed, we have seen in the greedy method. The knapsack problem that we'll use in the greedy method is a fractional knapsack problem. That is earlier what we have discussed is a fractional knapsack problem, which is solved via greedy method. We have shown that the greedy approach gives an optimal solution for this fractional knapsack problem. However, in the dynamic programming chapter, we are going to see 0-1 knapsack problem. So what is this 0-1 knapsack problem? In 0-1 knapsack problem, like in the fractional knapsack, we cannot broke the item, or we cannot take the fraction of the item. So here we are supposed to take the entire item, or we should not consider the particular item. Hence, in this particular 0-1 knapsack, so the value to be considered or the item to be considered is either 0 or 1. Either you are supposed to consider fully or should not consider. And while considering this, we are going to check the other constraints. That is, whenever we pick the item, then the corresponding weight should not cross the maximum capacity of the knapsack and should achieve the maximum benefit. These are the constraints that are common for the 0-1 knapsack also. But only condition differs is from the fractional knapsack is in fractional knapsack we can place the part of the item, and whatever the part of the item that you consider, that much benefit you will achieve. But in case of 0-1, either you are supposed to place the item completely in the bag or should not be taken. So this is what is called 0-1 knapsack problem. So this 0-1 knapsack problem cannot be solved by the greedy approach. The reason is here we cannot compare the sets because whether we have considered is the best solution or not in the fractional knapsack problem we can check, but we cannot make comparison with the previous one. So that is the reason we cannot consider or we cannot solve this 0-1 knapsack problem using greedy approach. So greedy approach does not ensure an optimal solution actually. Usually the optimal solution can be achieved only via principle of optimality, that by comparing the previous with the previous step. So we are going to use the dynamic programming to solve this particular problem. So here knapsack means the problem of knapsack 0-1 knapsack problem is the goal is to maximize the value of a knapsack that can hold at most W units, that is total capital W units. That may be that may be in case of Western terminology, it may be LBS or here we are going to consider as a kgs. So worth of goods from the list of items I0, I1, I2, and so on, In minus 1. So there exists total list of items. You are having a 20 kg bag and you have several items, and you are supposed to place these items in the bag, and each item is having certain weight, but every item along with the weight, the benefit is also available. That means, for example, you have a 10 kgs of cotton bag, and you have 1 kg of gold. So even though it is a 1 kg, but the cost is, that is, the benefit that you achieve is more. So that means even though it is a small weight, but sometimes it's the benefit of taking into the bag may be more. That is what we call benefit here, or the value is the value that we are going to consider. But whatever the item you take and place in the bag, you should not cross the weight. You should not cross the maximum capacity of the bag. But whatever the items you place in the bag must achieve higher value. This is what the main problem of the knapsack, that is 0-1 knapsack problem. So each item has two attributes. Value, let this be Vi for item that is I. Weight is let it be wi for item I. So that means for every item two values will be there. One is weight, another is value. Okay, so you should place this item into the bag so that the the consolidated the summed weight of all the items that you place in the bag should not cross 20 kgs, and you should achieve maximum value. So this is what the problem statement, that is knapsack, that is 01 knapsack problem. The difference between this problem and fractional knapsack problem is not is that you cannot take fraction of the item, as just we have discussed. You can either take it or not. Hence, the problem of the name is 01 problem. So we can also solve knapsack problem in a straightforward way. Just you try randomly the possible items to place, the possible items that are available that can be placed directly into the bag, and you can check for the whether you have achieved the higher value or not. This is called a brute force approach. So the general way of solving the problem, or the naive way of solving the problem, is to cycle through the all possible set of subsets of items, that is 2 power n subsets of items, and pick the subset with a legal weight that maximize the value of the knapsack. That means since we are going to consider all possible combinations, so obviously it takes too long time. So always the brute force approach will take too long time. And one more thing is brute force approach is nothing but a straightforward approach. That means without having any idea of how to place it, directly we'll try all possible things to place it. So it is just like there exists a switchboard. In switchboard there may be around 20 switches, and you want to turn on fan. So you don't know exactly what the fan switch is. But what you do is you try all possible switches. Whatever the switch with which the fan was turned on, that is the switch of the fan. So this is the way you will try checking. Okay, you may try checking from the front, or you may try checking from the last switch to first switch to last switch, and you may turn on middle switches. So you don't have any plan in this. This is what we call brute force approach, or we can say straightforward approach. Usually, in brute force approach, sometimes you may get the solution at the first moment, or you may not get the solution for a long time. Okay, the way of or the time taken to identify the solution is not guaranteed. So because there is no systematic plan in this. So it is just like you recall there exists around 20-30 switches. You don't know what is the switch of the fan. So obviously, sometimes whatever you by luck, whatever the switch you turned on, maybe belong to the same the fan. Sometimes even after doing all the things, okay, uh, over a period of time, you may not turn on the fan. So this is what the brute force approach is, in which the identifying of the problem is not straightforward. Sometimes you may get in the first instance, sometimes you may not get at all. So this is what the brute force approach is. So whenever you use this brute force approach, the time complexity will go up to order of 2 power n, because you are supposed to make 2 power n subsets. So we can come up with a dynamic programming algorithm that usually do better than the brute force technique. So now we'll see the how we can solve this via this dynamic programming problem. Dynamic programming problem will always indicate that the that means it works on the principle of optimality. What is this principle of optimality? Principle of optimality states that whatever is the initial state it may be, the next coming state must be better than the previous state. That means I have taken an item, and I know that the weight of the item and the value corresponding to that item. Now, whenever I place the item into the bag or knapsack, obviously, a knapsack is having the maximum capacity to hold. Say, for example, I am taking the item 1 which is having weight 3 kgs, and the weight of the bag is 20 kgs. So whenever I place this item in the bag, how many items that can I, how many items with how much weight I can place next in that bag? Obviously 17 items, because the maximum capacity of the bag minus the item that I have placed in the bag. So that is 20 minus 3, which is 17. So the next item, if I pick, I used to check whether the weight of the corresponding item is less than the remaining weight to be placed, and I will also see the maximization of the value. So this is the way we are going to compare, and whether if it is suitable, then we'll include that item into the bag. Otherwise, we'll try using another item. We'll try checking another item. If that another item was fitted, then we'll use that item into the place the item into the bag. So this is the way we are going to take multiple items and comparing with the previous stage, and we are placing in the knapsack. So as we discussed before, we are going to solve the problem in terms of subsets or subproblems. So what are the subproblems? First, I will consider first item, second item. Next, first item, third item. First item, fourth item. First item, fifth item. Next, second item, first item. Like how we are going to consider the optimal path in the all pair shortest path. In the same way, we are going to consider in this case also. So our first attempt might be to characterize the subproblems as follows. Let Sk be the optimal subset of the elements from I0, I1, and so on up to Ik. What we find is the optimal subset of the elements I0, I1, and so on Ik plus 1 may not correspond to the optimal subset of elements from I0, I1, I2, and so on Ik in any regular pattern. So basically, the solution to optimize the problem for Sk plus 1 might not contain the optimal solution from the problem Sk. So for this, we are going to take a simple example, and we'll go and discussing this, because if we discuss it theoretically, sometimes we may not understand this. So I'm going to consider a simple example that illustrates the point, that point with the example like this. So here are the four items: I0, I1, I2, and I3, and the corresponding weight of each item and the value corresponding to the item. So I0 is weight 3 and value is 10. Like that, I1 is 8 and 4, 9 and 9, that is I2, and I3 is 8 and 11. So all of you are requested to make note of this example on your in a register, so that it will be easy for you to compare uh, compare in the discussion. So the maximum weight of the knapsack can be holded is 20. So let us assume that the maximum weight to be holded is 20. The best the best set of items are, first one is I0, I1, I2. That means whenever you consider first three items, the best set of item is I0, I1, and I2 is I0, I1, I2. So that means 3 plus 8, which is 11 plus 9, 20. So 20 is the weight, so which can be fitted into the bag. But if you consider the total number of items as a whole, then the best set of items from I0, I1, I2, I3 is not the previous one, not the previous set, but we have achieved another set, because directly small number of sets are there, small number of items are there. You can directly visualize it and calculate it. Because here, if you look at the first three items, so 3, 8, and 9, obviously 20 is the weight we have achieved, and the corresponding value we have achieved is 10, 4, 14, 14 plus 9 is 23. This is the value we have achieved with this particular set. But if you consider these total items as is considered, then the suitable or best set is I0, I2, I3, whereas I0 is 3 and I2 is 9, which is 12, and I3 is 8, which is 20. So in the previous case also we have achieved 20, which is the maximum weight that can be holded, and in the second case also we have achieved maximum weight to be holded as 20. But what is the difference here? In the previous case, 10 plus 4, 14 plus 9, which is 23 is the value. But in this case, 10 plus 4, 14 plus 1, 11 is 25. 25 is the value. Even though we have two sets, but this second set is achieving 25 as a value, which is better than the previous step. So this is what the principle of optimality. Since it is better than the previous step, we are supposed to consider this set for our final inclusion. So in this example, note that the optimal solution is I naught, I2, I3 does not build upon the previous optimal solution I naught, I1, I2. So instead it builds upon the solution I naught, I2, which is really the optimal subset of I naught, I1, I2 with weight I2 or less. So because we have considered I naught, I1 and I2 previously, uh, and in which we have removed I1 and we have taken I3, thereby I naught, I2, I3 we have considered, and with this we identified that the value we got is 25. In the previous case the value is 23. That means we are going to make a small sets and we are going to check whether these small sets are giving us a better value compared to the previous subsets that we have considered. So this is the way we are going to cross verify that whether we are achieving the best value or not by making the condition that this is the weight condition that should not be exceeded. So this is what the basic idea of the knapsack problem. Now we'll see how this particular knapsack problem 01 by 01 knapsack problem is formulated and computed with some examples. So now we must rework the way we build upon the previous subproblem. Let the benefit of k comma w represents the maximum total value of the subset sk with weight w. Our goal is to find the benefit, that is benefit in the sense the maximum value that we are supposed to achieve. So benefit of n comma capital W, where n is the total number of items and capital W is the maximum weight the knapsack can carry. So our recursive formula for subproblem is like this. So you please make note of this recursive formula, because during the further explanation of this problem, this formula is very important because we are going to make the decisions based on this formula. It is the formula is just like this. It is a very simple formula. That is the benefit of k comma w will be evaluated like this. Benefit of k comma w is equal to benefit of k minus 1 comma w. K minus 1 means previous item comma weight. The current item's weight, okay, is the current items weight, current item comma weight. The corresponding value will be chosen, okay, as the previous value, as this previous item comma w, if the current item's weight is greater than the weight that is going to be considered in the current stage. That means you are going to take maximum weight, or you are going to take somewhat higher weight compared to the current stage. So in that cases, we are going to consider only the previous item weight. Then we are going to move forward. Otherwise, the maximum of benefit of, that is b of k minus 1 comma w comma b of k minus 1 comma the previous weight minus the current weight plus the value that we have considered previously, the value of the current item, whichever is maximum, that value we are going to consider and we are moving forward. Here unless until we don't know how much weight need to be added, we cannot take a proper decision. So that is the reason we are going to consider here w minus wk and the value of the corresponding item to be placed. So if whatever is the maximum, that value we are going to consider and place it into the bag. So in English, this means that the best subset of sk that has total weight w is the best subset of sk minus 1 that has total weight w, or the best sub of sk minus 1 that has total weight, the previous weight, that is w, minus the current weight plus the item key. So this is the cross checking we are going to do, and we are going to compute these values and moving forward. So finally, the recursive formula can be defined like this. The first case is like this: b of k comma w is equal to b of k minus 1 comma w if wk is greater than w, maximum of bk minus 1 comma w comma b of k minus 1 comma w minus wk plus bk, that is benefit of k. Otherwise, the best subset of sk that has total weight w either contains item k or not. That means either to place entire item or should not place. So the first case, wk is greater than w, the item k cannot be part of the solution if it was the total weight would be greater than w, which is unacceptable. In the second case, if the total weight is less than the weight, then the item k can be the in the solution, and we choose the case with a greater value. This is the formula of the 01 knapsack problem to solve. So I recommend you to make note of this formula, and this is the standard formula, recursive formula for solving this kind of problem using dynamic programming. And if you write the program for this, the same formula we are going to write in terms of a loop where n is the number of items, and we are supposed to reach up to the maximum weight of the. So first of all, we are supposed to initialize the weight w is equal to 0 to w, and b of 0 comma w is equal to 0. For I is equal to 1 to n, first of all, this is the initialization we are supposed to do. All the weights to be initialized to 0 and all the items to be initialized to 0. Then consider every item, and we are supposed to grow up to the maximum weight. Okay, and the formula here to be used here is if wi is less than or equal to w, then if vi plus b of I minus 1 comma w minus wi is greater than b of I minus 1 comma w, b of I comma w is equal to vi plus b of I minus 1 comma w minus wi. That is what the formula that we have considered previously, and the same thing we are going to use here. Otherwise, whatever is the benefit we are supposed to consider is the benefit of the previous item that we are going to consider here. So this is what the formula we are going to formulate here as a program. Everyone is recommended to requested to make note of this example. So we are going to take this example and go for the discussion in the next slide. Let's run our algorithm on the formula following data. Let there are 4 elements, that is n is equal to 4, and the maximum weight to be captured or maximum weight to be considered for the bag is 5. Now the elements and the corresponding values are like this: elements, weight and value. The first element weight is 2 and its value is 3. Second element weight is 3 and value is 4. Third element weight is 4 and value is 5. And next final element, fourth element weight is 5 and value is 6. Now consider this table. In this, these are the elements, and these are the weight, maximum weight to be achieved. So 0, 1, 2, 3, 4, 5. This is what the formula here. For I is equal to 1 to n, so we have used for I is equal to 1 to n, and for weight is equal to 0 to capital W. What is the capital W here? 5. So we are supposed to initialize the row with zeros and column with zeros. Initialize the base cases. For W is equal to 0 to W, B of 0 comma W is equal to 0. So we initialize this. For I is equal to 1 to n, B of I comma 0 is equal to 0. So we have initialized this to 0. Now, next one. The next one is currently I is equal to 1, because because 0th row is initialized with 0 only. Now we are going to consider the second one, that is the first element to be inserted. So whenever the first element to be inserted, I is equal to 1. So I is equal to 1, the value of I is 3, Wi is equal to 2, that is weight of this item is 2, and W is equal to 1, W is equal to 1, and W minus Wi is equal to minus 1. Here W is equal to 1 means the first, that means weight 1, okay, weight 1, because the maximum weight to be achieved is 5. So currently at weight 1, we are going to consider. So W is equal to 1. So W minus Wi is equal to minus 1, because 1 minus Wi is 2, which is equal to minus 1. Now, if Wi is less than or equal to W, Wi is 2, Wi is 2, which is less than or equal to W. So 2 is less than or equal to W. Is it true? No, false. So we directly go to the else block. In this else block, b of I comma W is equal to b of I minus 1 comma W. So b of I comma W is I is 1, W is 1. So 1 comma 1, b of 1 comma 1 is equal to b of I minus 1, that is 0 comma 1. So whatever the value is there in 0 comma 1, that will be directly placed here. The reason is the corresponding item cannot be directly fitted into the weight 1, because the corresponding item's weight is 2. We cannot do it. So we cannot calculate any benefit out of this. So directly the previous value, what is the previous benefit is there, the same benefit we are going to consider here. The reason is we are going to work on the principle of optimality. So we are going to take the previous items corresponding weight benefit. Then the same benefit we are going to consider if we are unable to fit the particular item in the cell. So this is what the first step. Next is, now the weight to be considered is 2. Now 2 is the weight, and W minus Wi is 0. 2 minus 2 is 0. So whenever this is 0, then we'll consider this Wi is less than or equal to W. That is 2 is less than or equal to 2. The condition is success here. The condition is true here. If the condition is true, then we are supposed to check this condition. Vi. What is Vi? Value of the item I. Vi is equal to 3. 3 plus benefit of, that is B of I minus 1. What is I minus 1? Currently I is equal to 1. I minus 1 is 0. 0 comma W minus Wi. W minus Wi. That is 2 minus 2. 0. 0 to 0 comma 0. So the corresponding value is 0 only. So Vi is 3 plus 0. 3 plus 0 is 3 is greater than B of I minus 1 comma W, which is 0. So 3 is greater than 0. So directly B of I comma W is equal to, we are supposed to place this value in that is 3. So here the maximum value that you can achieve once you place this item 2 is 3. So this is what the indication. Next, once it is done, then consider the second weight, consider the next weight for the item 1. So here 3. So 3 is less than 3 minus 2 is equal to 1, and Wi is equal to 2. 2 is less than or equal to W. Obviously, the condition is true. Whenever the condition is true, you are supposed to check for this condition. Whenever this condition is okay, then B of I comma W is equal to Bi, that is 3, plus B of I minus 1 comma W minus Wi, that is 0. So 3 plus 0 is 3. So you are supposed to place 3 here. Next, here also the same thing, because we are going to compare with the previous set here. So all the sets are all the values in the previous set is 0. So we don't find any improvement. So the same value 3 plus B of I minus 1 comma W minus Wi will be placed in the next stage. So till the weight 5. Next, we are going to switch to the second item. Whenever we switch to the second item, I is equal to 2. Vi is equal to 4. Why Vi is equal to 4? Because the value of the item 2 is 4. Whenever you place the item 2 into the basket or into the bag, then corresponding value you achieve is 4. So the corresponding value you will achieve is 4. So Vi is equal to 4. And the weight of this item is 3. Wi is equal to 3. And first we are going to consider check with the first weight. So weight 1. W minus Wi is equal to minus 2. So it cannot be fitted. So here W is 3 is less than or equal to the W1. So this cannot be fitted in this because it is greater than the value that we are going to consider. Not value, sorry, weight we are going to consider. So it is 0. So whatever the value is there, that we are going to straight away place here. And whenever we move to the 2, obviously 2 is less than the weight 3. So this condition fails and we'll go to the else block. And here whatever the previous stage value is there, the same value will place here. Next, whenever they consider weight 3, since 2 is having the weight 3, so 3 minus 3 is equal to 0 and 3 is less than or equal to 3, the condition is true. Now we are going to check Vi plus B of I minus 1. What is B of I minus 1? Currently I is equal to 2. I minus 1 means 1, comma W minus W. That is 0. So 1 comma 0, 0. So Bi is 4. 4 plus 0 is greater than B of 1 comma 3. So 1 comma 3 is 1 comma 3 is 3. So 4 is greater than 3. So whatever the value 4 you will get, that is the benefit that you are going to directly place here. So that means 3 exactly it will fit here. So exactly 3 will fit. Whenever exactly 3 was fit, then the corresponding benefit to be placed here 4. Next weight to be fitted is 4. Anyhow, already 3 was fitted here, so we cannot achieve more than this. So what to do is we are supposed to compare. We are supposed to check for the weight. W is equal to 4. Currently we are going to take, and the weight of the item 2 is 3. 4 minus 3 is equal to 1. So here 4 minus 3 is equal to 1, and we are supposed to check the condition here. Wi is 3. 3 is less than or equal to 4. The condition is true. Then if Vi plus B of I minus 1, comma W minus Wi. So higher high is corresponding is 2. 2 minus 1 is 1. So 1 comma W minus Wi. So what is the W? 4 minus Wi is 1. Sorry, 4 minus 3 is 1. So 1 comma 1. So what is the 1 comma 1 value? 0. So this 0 is it will be compared here. This 0 will be compared, added with the value of I, that is 4. 4 plus 0 is greater than B of 1 comma 4. So 1 comma 4 is, what is the 1 comma 4 value? 3. So whether this 4 is greater than 3. So since the 4 is greater than 3, directly whatever the maximum value is there, that we are supposed to place here. Next is weight is equal to 5. Whenever weight is equal to 5, what to be done? Same thing again, W minus Wi is 2. Whenever W minus Wi is equal to 2, obviously we are supposed to check here. Wi is 3 and less than or equal to W5. The condition is true. Then check for the value. Check for this condition. 4 plus B of 1 comma 2. B of 1 comma 2 is 3. So 4 plus 3 is 7. 7 is greater than 3. That is in the previous step. 7 is greater than 3 means directly the maximum benefit that you will achieve by placing this item is 7. So directly we will place here. Directly we will place in this particular position 7. That means whenever you place the item 1, you will get the maximum value. Whenever you reach the maximum weight of the bag is 3. Whenever you place the second value, the maximum value that you will achieve is 7. Next, consider the item 3. Whenever item 3 was considered, then obviously for every weight value, weight calculation, W minus Wi minus 3 minus 2 minus 1, these are less than the this with this condition will be failed. So whatever is the previous benefit that is directly placed in the for the item I. So item 3 for the weight 1 we cannot directly fit it, because just by looking at this weight itself we can directly say we cannot fit it. So previous benefit we are going to consider 0, 3, 4. Now since the weight of the item 3 is 4, so directly W is equal to 4 and Wi is equal to 4. W minus Wi is 0, and here the condition is true. Now we are going to check the value of I to be value of I, that is item 3 is 5, 5 plus the previous benefit. Whenever the previous benefit is I minus 1, that is 2 comma 0. What is 2 comma 0? 0. So this 0, that is 5 plus 0 is greater than 2 comma 0. So 2 comma 0 is 0. So 5 is greater than 0. So directly we are going to place here 5 here. Like that, we are supposed to consider for the 5. So W is equal to 5. 5 minus 4 is 1. And whenever this 4 is less than or equal to 5, here this condition failed. Whenever the condition failed, directly P of I comma W is equal to the previous benefit that we are going to consider here. In the same way, if you do for the fourth item, then as it is we are going to take the previous benefits, because the fourth item weight is 5. If you consider directly 5, the corresponding benefit that you will achieve is 7, because we are directly adopting from the previous stage. Now we don't have further things to consider. That means whenever you consider third item, then maximum benefit you can achieve is 7, and the fourth item also maximum benefit is 7. Now we are done. The maximum possible value that can be carried out in the knapsack is 7. Now we come to know that what is the maximum possible value that we can carry out is 7. So that means 7 is the maximum possible value that we can carry out. Now what we do is we'll find out what is the item that is suitable for placing in the knapsack, so that it will maintain the weight and at the same time which will achieve the maximum value, that is 7. Now this algorithm only finds the maximum possible value that can be carried in the knapsack. The value is B of n comma W. To know the items that makes this maximum value, we need to trace back through the table. So how to trace back through the table? Let I is equal to n and k is equal to W. If B of I comma k is not equal to B of I minus 1 comma k, that means the current stage benefit is not equal to the previous stage benefit, then mark the ith item as in the knapsack. Otherwise, else I is equal to I minus 1 and repeat further. So currently B of I minus 1, B of I comma k is equal to 7, and B of I minus 1 comma k is also equal to 7. So we cannot add these items in the knapsack. So move forward. So here also again B of I comma k is equal to 7 and B of I minus 1 comma k is equal to 7. So we cannot include these items into the knapsack. Now B of I minus 1 comma k is equal to 3. B of I comma k is equal to 7 and B of I minus 1 comma k is equal to 3. So it is not equal. When these are not equal, then mark the ith item as in the knapsack. What is the ith item? That is the first item to be placed in the knapsack, and I is equal to I minus 1, k is equal to k minus Wi. When k is equal to k minus Wi, obviously the previous corresponding element will be considered here. Then this particular thing will be taken into consideration. Then B of I comma k, because previously we have considered item 2 to be considered. Now 2 minus 1, that is I is equal to I minus 1. Now first item to be considered here. So B of I comma k is equal to 3 and B of I minus 1 comma k is equal to 0. Now these two are not equal. Then mark the ith item is in the knapsack. That is item 1 will be placed again in the knapsack. Then we have done, because we cannot go further. So k is equal to 0, so we have done. The optimal knapsack problem of the 0 by 1 knapsack consisting of the items 1 and 2, and will achieve the maximum benefit out of this. So whenever you place the item 1, the corresponding weight is 2, and whenever you place the item 2, the corresponding weight is 3. So 3 plus 2 is 5. The maximum benefit that you can achieve is 3 4, that is 7. 3 plus 4 is 7. So the 7 is the maximum benefit you can achieve, and the weight that you can include is exact weight that you can include is 7. But with all other possible combinations, we cannot achieve maximum more than we cannot achieve the weight as 5, but only with the item 1 and 2 we can achieve the maximum weight of the knapsack, and with the maximum value that is possible to achieve. So we are done with this k is equal to 0. So we are done. The optimal knapsack should contain item 1 and item 2. So if you analyze the time complexity for I is equal to W to W 0 to W, here since we are going here up to W weight, so the order of weight will be the complexity here in our program. And for I is equal to 1 to n, the time complexity is order of n, and repeat this for n times, so order of W, and so thereby the running time complexity of the item of this algorithm is order of n into W, where in case of if the weight is equal to the n, then it is n square, otherwise it is n into the weight. Remember that in the brute force we are going to take the 2 power n, that is we are going to try all possible combinations, we are going to achieve 2 power n. So with brute force with the dynamic programming approach, we have achieved the lower time complexity compared to the brute force approach. So this is the way this knapsack problem will be solved, and among all these things, the thing is you are supposed to remember the procedure, especially this particular formula. Whenever we have built up the table using this formula, then we need to apply back tracing to check whether which item to be included by comparing this item, comparing this condition b of I comma k is not equal to b of I minus 1 comma k. Then we need to consider that ith item and decrement the ith item by I minus 1. Then decrement the k is equal to k minus wi. Again cross check the condition, and like that you have to go down the above the table and identify which item to be included into the knapsack. So this is the way we are going to compare with the previous sets, and we are going to include whether the item to be included in the, we are going to take a decision that whether the item to be included in the knapsack or not. This is the 0 by 1 knapsack problem that can be solved via dynamic programming.